ladies and gentlemen, and welcome to this third highlight lecture of this IEC. On Monday, at the opening ceremony of this IEC, you could witness the bestowal of the 2024 IEF World Space Award that was given to the Chandrayaan-3 team of ISRO. And now you will have the opportunity to hear a highlight lecture titled New Frontiers in Lunar Exploration, Chandrayaan-3 Mission and Beyond. This highlight lecture will highlight the successes of the Chandrayaan-3 mission and will give us more insights on the next steps of India's space missions. And it is my great pleasure to announce that this session, this highlight lecture, will be opened by the IEF President, Clay Mowry, who will give opening remarks. So please welcome Clay on the stage. And let me also remind you that you will be able to ask your favorite questions through our Slido system again, hashtag IEC 2024. So please make use of that and ask your questions. Clay.
Thank you. So thank you, Christian. It's a pleasure to be with you here today. Good evening, distinguished guests, and thank you for coming to this lecture. It's a great honor to welcome you all to this session, New Frontiers in Lunar Exploration, the Chandrayaan-3 mission and beyond. It's a remarkable milestone in space exploration. As Christian mentioned earlier, it was the World Space Award that was given for 2024, which is our most prestigious and highest honor given by the Federation. And to have Dr. Somanath there to receive this was a great honor for me to be able to present that award to him at the opening ceremony. It's an achievement, and it's now immortalized as National Space Day in India, which I think is a lovely gesture. It's a testament to the visionary leadership and scientific excellence of the Indian Space Research Organization. I had a chance to visit ISRO a year ago and to see the amazing work they're doing. It's an amazing place. If you ever get a chance to go to Bangalore, to Bengaluru, as they say, and visit, it's something to behold. The mission was launched on July the 14th of 2023, and Chandrayaan-3's journey from its precise orbit insertion by the LMV-3 launch vehicle into its flawless execution of its landing and rover operations demonstrates the strength of the amazing engineering team at ISRO and the program team. Not only has the mission advanced our understanding of the moon's composition, revealing elements such as aluminum, sulfur, and titanium, it has also contributed significantly to lunar geology. The mission's success has inspired curiosity and excitement in space around the globe, but also in India. And I think it was an amazing accomplishment to see people cheering in the streets after this. And now they've announced, in fact, their intentions not only to do human spaceflight with the Gaganyaan system, but also to build a space station and to land on the moon in 2040. I mean, what are you guys are doing a lot, huh? It's amazing, the ambitions right now for ISRO, but they're building on a tremendous success. So, as we look ahead to the future of lunar exploration, let's take a moment to reflect on the significance of the Chandrayaan-3 mission, not just for India, but for the entire community. It's a powerful reminder of how exploration continues to push the boundaries of human knowledge, to foster collaboration, and to inspire new generations to reach the moon and the stars. So I'm very honored now to be able to introduce the highlight lecture and invite on stage the project director for the Chandrayaan-3 mission, P. Veeramuthuvel. Please join us on stage.
Thank you, President, for the introduction. Good evening to everyone. Can you go to the next slide? Okay. So I'll be covering 5 topics today. The evolution of Chandrayaan program, then Chandrayaan-3 mission, the architecture and the configuration and how we achieved this mission. And then later I'll talk about the outcome, science outcome, and Chandrayaan-4 and Chandrayaan-5, the near future missions, and also the future of Chandrayaan program. As already told that by 2040 we have to have a crew landing onto the moon. So the Chandrayaan-3, we had orbiter around the moon. It has detected the water molecules, which was the main highlight, and we had a lot of thirst to going to moon again, and it was largely successful. And followed by, we had a Chandrayaan-2, which had two objectives. One is orbiter, which carried high-resolution payloads compared to Chandrayaan-1 orbiter, and also we had a lander and rover. The Chandrayaan-2 orbiter is very successful, even though the designed mission life is 1 year, but it is more than 5 years over, but still it is giving a plethora of science data, whereas the landing objective could not be met. Hence, Chandrayaan-3, we had a specific lander and rover. We also had a host of scientific instruments in both lander and rover for an in situ scientific measurements. And upon the successful completion of Chandrayaan-3, the next logical step is to bring back the sample from the lunar surface and safely bringing back to Earth. That is the aim of Chandrayaan-4. And Chandrayaan-5 is a LoopX mission, which is having a collaboration with JAXA, ISRO-JAXA collaborative mission, will be aimed for a precise landing onto the South Pole with the bigger lander and rover, and also it will quantify the water molecules and quality of the water molecules, and a lot of scientific instruments which will be having many studies like composition studies, elemental composition studies, many studies, which I will be covering in the subsequent slides. Coming to the uniqueness of Chandrayaan-3, the first thing is it is made in India, the launch vehicle, satellite, and also the technologies, and the entire mission design and the configuration and also the mission trajectory is all, it is made in India. And the first, we were the first country to go to the higher southern latitude region, which is 70-degree latitude towards south. And also we had a very advanced technologies, particularly on the sensors and propulsion system, as well as the navigation, guidance and control. And also we had advanced payloads, which is having a compact volume, mass and power. We had 6 instruments on board lander and rover, and also a compact rover, which is 25 kg of mass, which traveled around 101 meter from the landing point, and it had inbuilt functions of all the systems, including the mobility system. And coming to the mission elements, we utilized LVM-3, that is the heaviest launch vehicle we have with ISRO, which has put the craft into a GTO orbit, which is 36,000 kilometer altitude. And from there, the propulsion module has taken the lander and rover all the way to the moon and separated the lander and rover. And rover is accommodated inside the lander, and the lander mass is approximately 1.75 tons. And the remaining mass comes from propulsion module. And rover is, as I told, it is a 25 kg rover approximately. And 3 distinct objectives we had. One is safe and soft landing to the designated targeted point. Then rover roving on the surface and conducting an in situ scientific instrument measurements. And coming to the mission profile, we had launch on 14 July, and we left towards moon, that is a translunar injection on 31st July, and we captured the moon on 5th August, and 17th August we separated the lander and propulsion module, and we landed finally on 23rd August. And we also utilized the DSN network apart from our IDSN. One is the JPL. They have provided an excellent support. 3 stations they have provided support. One is Goldstone, Canberra and Madrid. In addition to the network support, they also supported with us navigation, OD process, and validation of our trajectories and so on. And thanks to JPL team who have supported us in this mission. And also the ESA team, they have given 2 ground station DSN network. One is Kuru and Gunili. And they also supported in various mission phases, right from EBNs, LBNs, and post-landing scenarios. And these are the 4 power descent phase. The first phase is a rough braking phase, which the craft traveled from 30 kilometer to 7.4 kilometer. And there is the next phase is an attitude hold phase, which we constrained the attitude for the altitude measurement, and the next phase is the fine braking phase, which travels from 6.8 kilometer to nearly 800 meters or 1,300 meters, depends on the mission scenario. And finally, we call the fourth phase is called the terminal descent phase, where the lander travels vertically down. At the 150 meters height, there will be a hovering, which means the lander will be compensated with the thrust in upward direction, and there is a mass into gravitation force acting downward, and there is a hovering of about 22 seconds. During this time, the sensors, a set of sensors will come into operational. One of the important sensors is the hazard detection and avoidance sensor, where we will be taking a picture, and prior to landing, we had stored image from our orbiter high-resolution camera from the Chandrayaan-2 orbiter, which characterized the landing site thoroughly before the launch. And this image, the onboard image, will be compared, and there will be an algorithm which will avoid the obstacles. And based on the targeted coordinates, it can have a vertical descent or it can have a retargeting. And at 10 meters height, there will be a constant descent. We were targeting 1 meter per second in the vertical direction. And this is how the power descent profile looks like. There are various velocities and the altitude profile with respect to time. And for our performance on the day, we had a pinpoint landing. We achieved a nominal landing. I'll be covering what is off from the targeted landing site. And coming to the enhancement in lander's robustness compared to Chandrayaan-2 lander, we had various improvements in the lander. One is the landing site area. In Chandrayaan-2, we had a 0.5 by 0.5 kilometers area. It was a very stringent in terms of size, whereas in Chandrayaan-3, we had a bigger area with the size of 4 kilometer in along range and 2.4 kilometer in across range. This was thoroughly characterized by OHRC camera from Chandrayaan-2 orbiter. And also we designed this time a multiple descent trajectory. If one sensor fails, what is the next option? If one engine fails, what is the next option for us? So there are several mission paths, as high as 9 mission plans we had to ensure that it takes care of the wider dispersion bands. And we also improved several algorithms in the navigation and guidance domain. One is the thrust and angle continuity between the phases as well as within the phase. As I was telling, 4 phases we had in the power descent phase. All these phases, we had a smooth thrust profile as well as angle profile. Almost we have to have a pitch maneuver of 90 degree from 30 kilometer till touchdown. So all these angle and thrust continuity we ensured. Appropriately, the polynomial algorithm was chosen. And also we had, as I was telling, it handled the wider dispersion ranges. And we used an additive dispersion limits compared to Monte Carlo. We go for a 3 sigma Monte Carlo simulations. This time we adopted an additive extreme cases as well. And also we enhanced the touchstone limit. Earlier we had 2 meter per second in vertical direction and 0.5 meter per second in horizontal direction. This time we improved from 2 to 3 meter per second and 0.5 meter per second to 1 meter per second. And also the 12 degree slope angle, it can tolerate, the stability can have up to an angle of 12 degree. And we built full redundancy this time. Some of the redundancies we did not have due to the resource constraint, that also was overcome successfully. And also we improved several sensors algorithms as well as the design aspects. One of the new sensors we developed this time, that is laser Doppler velocimeter, which gives a 3-axis velocity information, which is also insensitive to the terrain, unlike visible sensors, which is very sensitive to the sun angle and the illumination conditions. So this is something, a very state-of-the-art sensor, which is successfully developed and flown this time. And another thing is the propulsion system. We have also improved a lot of the technologies in the propulsion system. The first thing is it is a throttleable nature. The thrust is varying from 800 Newton to 400 Newton. We used 4 such engines. And in addition to that, we have loaded more propellant to handle wider dispersions. And also we have put anti-slosh baffle. As you know that when we were traveling from 30 kilometer till touchdown, there will be a lot of deceleration coming onto the craft. So in order to avoid the slosh effects, we have put anti-slosh baffles inside the tank. And also we have strengthened the IV&V software cycle, and we developed several simulation test beds, which I'll be talking in the subsequent slides. And the ground test beds, on the left side you can see various simulation test beds which we have developed. One is the autonomous 6-DOF simulation. This is basically a digital simulation, which we also come up with the new test cases, and also I was telling the additive dispersion cases also we brought in compared to the Monte Carlo simulations. And also the software in-loop simulation. This is the first time we developed, where we have a different software, one in simulation test beds, other one in onboard. So in order to overcome this kind of differences, we have come up with a software in-loop simulation, wherein this software-related problems can be surfaced out in the ground itself, and also onboard in-loop simulation, which is a very regular for our all satellites, and also hardware in-loop simulation. On the right side, you can see several tests. One of the important tests is the integrated cold test, where we flew all the sensors, which gives position information and velocity information. And we flew in the helicopter, wherein we created artificial craters and boulders in one of our test site, where we gave necessary dynamic conditions like altitude and velocity, and all these sensors were operated in a seamless manner. And the navigations also, several types of navigations we had, like inertial navigation, absolute navigation, local navigation. All these navigations were also thoroughly characterized during this test. And the second important test is, having characterized the sensors and navigation, we have to put the propulsion system in closed loop, for which we devised a test called integrated hot test. This is another important test which we have created in Sriharikota, which is our spaceport, where we have to conduct this test in a conducive environment. And we made a special test site and special test setup for conducting this test. And having done both the test, ICT and IHT, we finally moved on to the touchstone test. We simulated a different touchstone conditions, like simulating vertical velocity, horizontal velocity, as well as flat terrain or a slopy terrain. The terrain can be hard or it can be soft. Under different touchstone conditions, we have done a series of tests to assess the strength and stability of the craft. And also the hardware simulator. That is another important test. Before the launch, we have made another setup, which is basically another satellite, set of a satellite, which will be simulating all these hardware conditions, sensors, navigation, guidance, control, propulsion system. Everything is in loop. Before we do any commanding, we do simulations in ground, and we uplink those commands so that we ensure that no wrong commands are sent, and also we ensure that the flight parameters are thoroughly tested. As I was telling about these 3 tests, which I will skip now. So this is, you can see on the visuals, this test on the left side is an ICT test, where the helicopter is coming down with the required dynamic conditions. I was telling in the previous slide, we were coming from 30 kilometers till touchdown. So there was a attitude hold phase, which starts from 7.4 kilometer altitude till touchdown. So that condition were simulated using an helicopter, and helicopter it can hover. It can literally stay there. So for that, we hired an helicopter from that point of view, and we operated the sensors in different conditions in which the sensors can come during the power descent phase. So a host of test cases were conceived and tested successfully. We had a lot of hiccups during this test, but it gave a lot of insights for the success of this mission. And the entire test site is newly created with a lot of craters, artificial craters and boulders, which mimics the actual moon condition. And also we had a flight equivalent sensors, NGC system, TMTC system, and also we had the navigation. To characterize the onboard sensors, we had a reference sensor, which is 1 order better for characterizing the position sensor as well as the velocity sensor. And we used different kinds of a sensor for providing or correcting the inertial drift during the descent path. And also the test site also we created with the DEM, with an accuracy of 0.1 meter accuracy, first time. And also the landed drop test. We created a lunar soil simulant test bed, which mimics the anorthosite properties of the lunar rock. So that kind of a test bed is created both flat terrain as well as in a 12-degree slopey terrain. And also we created a swing mechanism which will give a necessary horizontal velocity. The vertical velocity is achieved just by dropping based on the potential energy. The kinetic energy can be achieved, but to offer a horizontal velocity, we created a swing mechanism, and also we created, in order to have the difference in G conditions in the moon, as we know that moon is 1/6 of Earth's G, so we scale down the model to 1/6 of mass, and also achieve the longitudinal CG to equivalent to the flight model, so that the stability is achieved perfectly. And you can see the visuals on the right side, where the actual lander was dropped to assess the strength condition. And also we have put a touchstone sensor, which is again a unique design. Below the foot pad, we have a leaf spring. Upon the touch condition, the sensor will come into contact, and the closed loop will be terminated, where the engine firing will be terminated. So that also was successfully tested as part of this drop test. And these are some of the mission timelines when the project was approved. It was approved in Jan 2020, and we had a series of design reviews. You can see in the bottom where the tests were conducted. These are the 3 important tests I was mentioning: integrated cold test, hot test, and lander leg drop test, which was thoroughly tested in a almost. We have consumed a lot of time during this ICT test and IHT test, and which gave a lot of inputs, and that was used effectively for retrofitting activities in the flight model. And also the flight model was realized successfully. Propulsion module was realized in April 2020, which was the first system was ready, and then the rover was ready. Finally, the lander was ready by February 2023, and May we have made the spacecraft ready, and it has moved to launch site, spaceport. And finally, the launch took place on July, and the landing on 23rd August. And coming to the landing performance summary, we had as I was telling, it's a nominal launch. Every health of the systems, all the mainframe systems were nominal as expected. And also, we have seen the thrust continuity and angle continuity was intact, and the closed loop NGC algorithm flawlessly worked, and we were just off by 170 meter in along direction, and 300 meter in 170 meter in across direction, and 300 meter in along direction with respect to the targeted site. And on the right side, you can see the thrust profile, acceleration profile and thrust profile, which was matching one over the other with respect to the predicted as well as the achieved plots. And this is some of the plots where you can see the horizontal velocity with respect to time, vertical velocity with respect to time, and the sensors with respect to time. All were actually within the bounds, within the 3 sigma bounds. And this is where we landed. The landing finally happened at around 69.3 degree latitude towards south and 32.3 degree towards east. And we had a mission life of 1 lunar day because we were heavily depending on the solar power. We did not have a nuclear resource. And this is captured by the Chandrayaan-2 orbiter, where you can see the lander was captured just before the landing and after the landing. We have taken a picture from OHRC, and that has captured very well. And on the right side, you can see some of the images coming from LRO and KPLO. And coming to the scientific part of it, we had 3 payloads in lander. One is instrument for lunar seismic activity, and CEST, that is called the Chandra's Surface Thermophysical Experiment, and RAMBA, Langmuir probe. And one more payload, it is a passive instrument which is from NASA, that is a laser retroreflector array, which is just, it will give a fiducial markers, and we have put this particular instrument on top of the antenna so that it is visible to the orbiter from NASA mission. And coming to the rover payloads, we had 2 scientific instruments. One is APXS, that is alpha particle X-ray spectrometer, and second one is LIBS, that is called laser-induced breakdown spectroscopy. As a value addition in the propulsion module, even though the main job of the propulsion module is to carry the lander all the way to moon, but as a value addition, we have put a payload called a SHAPE, that is a polarimetry payload. We know that this payload is mainly to look at the Earth from the moon. We know that Earth is an habitable planet. if you characterize the signatures thoroughly, which can be used in the future interplanetary missions so that we can look for a planet 2, Earth planet 2, such things. And coming to the payload instruments, it is not a static instrument. All are deployable in nature. On the left side picture, you can see here, on the screen, you can see here some of the visuals from the rover camera as well as from the lander camera. In the picture, you can see on the ILSA marking where this instrument for lunar seismic payload is dropped onto the surface. As you can see there, because it has to measure the seismic event. It can be natural, it can be artificial. And on the left side, there is a chase payload. This is a probe which is inserted into the lunar regolith. So that also was captured by one of the camera from rover navigation camera. And you can see on the bottom picture where this probe, it is called a Langmuir probe, which is sitting on the top deck of the lander craft, which is away from 2 meters from the surface. This is also a deployable payload. There is a shadow you can see. This payload is deployed because it has to be away by 1 meter from the lunar craft. And rover also has got 2 payloads. One of the payload is a deployable nature. This is called an apex payload, alpha particle X-ray spectrometer. This is again, it has to go near to the surface. As you can see on the right side, this is again, it can deploy from 0 degree to 90 degree, and again it will come back to 0 degree whenever the rover travels. And once the rover is static, again this payload is deployed, conducts the measurement, and transfer the data. And this is a very important thing, the rover path planning. So on the right side, you can see where the lander landed, and rover has traversed, as I was telling, it is almost traversed 101.4 meter. And we had multiple challenges for the rover. Unlike lander, rover it works on semi-autonomous way, because rover cannot communicate directly with Earth. It has to communicate via lander, which means the rover has to take a picture through the navigation camera, and it has to send to the ground through lander, and we do a path planning. All this DEM and the path planning is done on the ground, and once the path is clear, whether we have to take a right turn or a left turn, or it can be straight, all these things will be decided in ground, and appropriate commands will be uplinked to the lander, and in turn the lander will communicate with rover for a next point from point A to point B. This is how the entire rover was operated using ground intervention, and entire 24/7 in that one lunar day was operated continuously to maximize the payload operation. And you can see on the left side also, one of the important thing is the craters. You can see this craters, the picture was taken by the rover camera. As I was telling, it's a navigation camera. This crater was successfully negotiated. I would not say negotiated, it was successfully avoided, because the rover is very tiny. It is 25 kg of rover, and we had multiple challenges. Unlike lander, we have a tiny solar panel, and again it is depending on the solar power condition, and it has to track the sun. The sun is also moving in nature. From the dawn to dusk, it is moving in azimuth direction as well as in elevation direction. So hence the rover solar panel has to track the sun continuously. And we also retraced on the right side, you can see how the rover has retraced back. This also was taken by the picture, and we successfully avoided this crater. And also the lander itself is a threat to the rover, because we went to the pole, even a small, because of the small sun elevation angle, even a small height will cast a long shadow. So that also is a threat. So we had multiple challenges while operating this rover, and with all that, we have operated the payload, both the payloads and rover successfully. It has given a lot of science data. Now coming to the science aspects, we had the first instrument is on ILSA, which measures the seismic activity. There was a high sensitive vibration accelerometer in all the 3 directions. It senses the ground vibration. So you can see on the right side, there is a picture where the ground acceleration versus time. We had multiple events. It can measure the magnitude, frequency, as well as the sensitivity of the instrument. All these things was measured, but largely the artificial event, the magnitude was more when the rover is traveling on the surface. Because of that nature, it has given a large magnitude, and we know that can be correlated because it's all an the event which took place artificially, and also the payload deployment, it's an artificial event. On the bottom picture, you can see the red color curve, where it's an uncorrelated event, where it could be a natural event, where the moon quakes can be there, or some meteorites impacts could have been there. Almost 50 instances we saw this kind of a natural event, and this instrument can measure from 1 micro-G to 5 milli-G kind of a range. And also, the another important instrument is a CEST, where the probe is inserted into the regolith for about 100 mm, and every 10 mm we have put a temperature sensor which can measure the temperature. You can see a strong vertical gradient, where you can see in this picture, where a strong vertical gradient from the surface to the subsurface. We have seen at the surface around 50 degrees centigrade. As we go inside to the depth of 0.8 centimeter, that is 80 mm, we have seen the temperature drop to minus 10 degrees centigrade, which shows that the regolith is having a poor thermal conductivity. And this gives a lot of insights how it's going to go into deeper in the days to come, how this input will be very, very useful for the future missions. And on the bottom side, you can see with respect to time at different temperature sensors, as I was telling, 10 temperature sensors we had, and different sensor measurements over time also is recorded here. And the next instrument is a Langmuir probe. This is again a state-of-the-art instrument which measures the lunar near surface plasma environment, where it can measure the plasma density and temperature. We have seen a good amount of plasma there in the high southern latitude region as well. We know that a lot of measurements was done in the equatorial belt, but on the high latitude southern region, there was no measurement, and this gave a lot of inputs, and this will be very useful for the future radio wave instruments, how it's going to affect the polar region, how it is going to affect. And we saw that good amount of almost 380 to 500 electron density per cc was measured from this instrument. And the next instrument is the alpha particle X-ray spectrometer, which measures the major and minor rock forming elements. There are various measurements was done from the elemental composition point of view: magnesium, aluminum, iron, the titanium. There are many electron. This composition was measured. Based on that, we have also derived the chemical composition from the elemental composition, and you can see on the right side where a lot of minerals were also derived from the elemental composition. And one of the very important thing is, we saw that the regolith is made of two major rock forming elements. One is the ferron anorthosite and magnesium soot. This is again confirms the lunar magma ocean theory. That hypothesis, it validates that hypothesis. And also one another important thing is, we have also seen the magnesium rich minerals on the surface, which is eventually coming from the mantle due to during the formation of South Pole Atkin Basin. This is one of the very important finding from this instrument. And another instrument is, it works on the laser based principle. It works with the frequency of 150 nanometer and with the spectral signature of 220 to 500 nanometer. And this also is a complementary to the APXS payload, the previous slide what I was referring. And this also confirms that the major minerals and minor rock forming elements. And as I told about the shape payload, which is basically to look for another planet, whether it is livable, by looking at Earth from the moon, which gives a subtended angle of 2.5 degree. We had a FOV of 2.5 degree, which covers the entire disk of the Earth from 4 lakh kilometers. Once this instrument was successfully used, we know the characteristics of the Earth, and this can be used for the future planets in the future interplanetary missions. And I was telling about validating about the lunar magma ocean. We saw that one of the discovery is the buried crater, where you can see on the left side picture where the lander landed, the star mark where it indicates where the lander landed, and the arrow marks of the black color arrow mark indicates the circle, the semicircular structure of the crater, which is almost 160 kilometer in size, semicircular in nature, and 4.4 kilometer deep. And this theory shows that it is all settled with the multiple impacts. And these data are available in public. It is there in portal, and so many countries are utilizing this data, and so many users are there already. And a lot of publications are already available, and future publications are also on the way. A community can use this data effectively. And after completing the science aspects, we also did another important experiment just before the mission life was over. We did a hop-on test, which is the lander was the engines, whatever is used to land, the same engines were fired again just to elevate from where it landed, and it also laterally moved, so that we wanted to make sure that all our engines are working. This will also act like a precursor for the Lunar sample return mission. This is our next mission, and we have successfully demonstrated this. We did not have any plan just before landing. We have done everything in 24 hours time, and we made the software ready, we made the algorithm ready, and we did this experiment, and it really exceeded the mission objective. And coming to the near future Luna experiment programs, we have Chandrayaan-4. As I told, it is a Luna sample return mission. We are primarily aiming to bring the sample back to Earth safely. Carrying out this mission, we have multiple modules are required. Again, we have to achieve this mission with our own launch vehicle. So I'll be covering about the challenging part of it and some of the mission concepts. And Chandrayaan-5 is basically a LoopX mission. Again, it's an ISRO-JAXA mission with a bigger lander, bigger rover, and we are also aiming exactly onto the pole. We also finalized the landing site, and we have also in the process of finalizing the payloads. We have already some of the payloads on board in both lander and rover. And coming to Chandrayaan-4, this is one of the very ambitious mission for us. Which will also demonstrate our capability for the crew landing mission. First level technologies it will demonstrate, like we have landed, now we will be coming back from surface to the moon orbit, and again from moon orbit to the Earth orbit, and finally we will be coming to the Earth, crossing the atmosphere. So we have to have necessarily multiple modules to achieve this, and this also calls for 2 stacks. So each stack will have a mass of around 4.6 tons. That means 9.2 tons of entire spacecraft mass. So we are achieving this with 2 launch vehicles, that is LVM-3 vehicles, and we also have to achieve this mission with several docking and undocking in the Earth orbit as well as in the lunar orbit. And several new technologies are required, like we are aiming to go deep into the moon with 2 meters depth, where we want to collect the subsurface samples, as well as we want to have some kind of a robotic mechanism where it can scoop from the surface also. So we are planning to bring something like a 3 kg of sample, both it contains both surface as well as subsurface sample. And also we have to have a technology of sample sealing, sample cartridge mechanism, and also we have to successfully transfer the sample from one module to another module. It also calls for different kinds of a technology. All these technologies we have taken up, and we will be demonstrating in this mission in Chandrayaan-4. And also, as I told, we are aiming again in this mission the latitude between 85° to 90° latitude, and a lot of studies are going on to finalize one of the location. And coming to the mission concept, as I told, we are having a 2 launch vehicle, and both the modules will get docked in the GTO orbit, and all these modules will travel together to moon, and some of the modules will stay on the moon orbit, and some modules will go to the surface and collect the sample, and one module will take off from the surface, comes back to the orbit, lunar orbit, and it docks with the lunar orbit, which is already another module is parked there, and it will transfer the sample from the ascent module to the transfer module, and finally the ascent module will get undocked, and the transfer module and re-entry module will come out of the moon sphere of influence. It will come back to Earth. That we call it as the trans-Earth injection. And finally, the transfer module will eject the re-entry module, and only the re-entry module will enter into the Earth's atmosphere. And finally, to the targeted site, we will be bringing back the sample with the aim of 3 kgs of mass. And coming to Chandrayaan-4, that's a LUPEX mission. Here we have responsibilities from ISRO side is the mission planning, the entire mission planning, the trajectory design, as well as the entire lander design. And there will be a payloads from either side, and as well as the JAXA will have a primary responsibility of rover, the big rover development, and also the payloads, which will be coming from both sides, as well as the DSN network, and as well as launch vehicle. And here we are aiming a safe and precise landing to the targeted site, which is the connecting ridge of the landing site, that is called 89.45 degrees south and almost 222.8 towards east. And this mission will have bigger lander and bigger rover with more payloads, more scientific instruments, and this will be first time targeting to the permanently shadowed region, and the rover will travel from the lander where it lands, and it will traverse to an extent of 500 to 1 kilometers distance, and there will be a lot of in situ measurements, and we are also aiming for volatile measurement as well as the quantification of water and quality of water and many things. And also we have plans to go up to 1.5 meter deep. And some of the mission concepts where the JAXA launch vehicle will inject the craft with a bigger elliptical orbit, almost 1.4 kilometers, 1.4 kilometers orbit, and from there we have to reach to the moon, and again the lander propellant will be spent, and finally the landing and other approaches will be similar to Chandrayaan-3. And finally, we will have a rover which comes out from the top deck, and the rover will go on the left side. You can see the rover traverse path where we will have science measurements, scientific instruments where it will measure a lot of scientific measurements are planned. And some of the spacecraft views you can see here, the stowed and deployed views, and the rover is sitting on top of the lander. This is a very heavy lander with a rover mass of 350 kg mass, and this mass has to come down to the surface, and we are going to have a different kind of the deployable mechanism, unlike in Chandrayaan-3. Chandrayaan-3, the rover was placed vertically inside the lander, and the ramp was opened out. Here, the rover has to come from the top deck, and also we have a bigger lander. The technology itself will be different, and also the landing leg technologies where we have to absorb more energy because the mass is increased, and we also have to have the same stability. So many new technologies will be put in this Chandrayaan-5 LUPEX mission. And rover payloads, I'm not going to read. There are many payloads from ISRO. Some 4 payloads are there, ground penetrating radar and IR spectrometer, and there are many payloads from JAXA as well. And also, in addition to that, we will have a payloads on the lander as well, which is all in the is in the process of finalization. And coming to beyond Chandrayaan-5, we have various missions. One is on the top side, you can see the initiative point of view. We have already have a Gaganyaan program where we will have a 3 uncrewed mission and 1 crewed mission. And this is something we are targeting to complete by 2026. And beyond that, we will have the Bharatiya Antarakshi station. We will have our own space station around the Earth. And already Government of India has approved the first module. And we will have 5 modules in this. And we plan to set up this all these 5 modules by 2035, and the first module is slated for something like 2028 is targeted. And on the technology point of view, there are various missions are required to achieve this primary goal. So we will have a docking. We have an upcoming mission called SPADEX, which is going to be docked in the circular orbit. Almost this mission is getting ready now. And future, we have to have an elliptical orbit docking as well. So circular orbit docking alone will not meet our future requirements. So we have a series of SPADEX mission. We have SPADEX 2 and 3, which will primarily aim for elliptical orbit docking, which is also required for a Chandrayaan-4 mission. This will act like a technology demonstration before the Chandrayaan-4 mission. And also we will have many missions like long-term survivability on the surface. We will be utilizing many instruments for ISRU purpose and as well as for science purpose, and we may have to utilize the nuclear resources for long-term survivability, and also we should come up with the new technologies for going to the South Pole, exactly onto the South Pole, because the sun elevation angle will be very low, and how these algorithms are going to work and the sensor is going to work, for that technologies are required. And also we have to have relay communication satellites as well as navigation satellites. Like ESA Moonlight program, we also have a plans of having a set of satellites around the moon with an highly elliptical frozen orbit, because we are targeting our landing site towards the South Pole. So we will be aiming between -70° to 90° towards south. So we may have to have a set of satellites which will act like an infrastructure around the moon. And going beyond 2035, we also have on the top side, you can see the entire Bharatiya Antarakshi station will be ready, and that will be utilized effectively for further going to the moon. And we will have a crew orbiter around the moon. Before that, we will have an uncrewed orbiter. We will have something like one uncrewed orbiter, which will be identical to the lunar orbiter. And once it is demonstrated successfully, the final phase, this is another important target in which we are working. By 2040, we want to have our crew lunar lander onto the surface. So before that, we will have an uncrewed lunar lander, which will be identical to the crewed lunar lander. And beyond that, it is again an expansion phase where sustainability is very important. So we may have to extend this Bharatiya Antarakshi station to something like a lunar gateway, where we can utilize the lunar gateway which is already set up from the Artemis program, and we may have to have some reshuttling between the Earth to the orbit around the moon, as well as some reshuttling is required between the orbiting around the moon to the surface. And we have to have a vehicle which will have a pressurized condition, and there will be a lot of transportation between Earth and moon with the vehicles, with cargoes, so many things. And also we have to build lunar stations, permanent lunar stations, and set of instruments are required before that, how to convert this regolith into the construction material, and how to bring the habitability, so on. So all these things are planned beyond 2040 as well. Thank you for the patience.